Hey folks, welcome back to the webinar series here with Beaumont Technologies. I'm Jerry Rooney, and today I'm going to be walking you through another internal study we've done, this time looking at hot gate insulation properties and asking, is the default assumption within Moldflow a safe assumption? So a little background on me. Again, I'm Jerry Rooney. Some of you folks may have worked with me over the years on phone calls and things, looking at simulation projects. I'm a design engineer here with Beaumont Technologies. I've been full-time since December 2016. Before that, I was an engineering intern with Beaumont from 2014 to 2016 while I was attending Penn State Behrend. I got my Bachelor's of Science in Plastics Engineering Technology from Penn State University. Uh, Went on to become expert certified in Moldflow software. And more recently, within the last few years, I went through American Injection Molding Institute Plastics Technology and Engineering Certificate Program. So, for those of you familiar, we have AIM, or the American Injection Molding Institute, here at Beaumont, which is our educational branch. And they have this PTE, or Plastics Technology and Engineering Program, which is a very concise version of a plastics education you might get from Penn State Behrend, for example. But it's done within, I believe, 9 months over the course of several different courses with mold design, part design, materials, all that sort of stuff. And it's a really great, concise education of plastics. And for me, it was a really good refresher of a lot of stuff and honestly deepened my understanding of a lot of different plastics aspects, and it's been super helpful for me in my career and working with simulation and just kind of it gives you a very broad understanding of plastics in all their aspects. So it's just very helpful. So I recommend it really highly. I speak very highly of it all the time. You can reach out to Dave Hoffman if you're interested in that program, or just get in touch with the AIM Institute. So I always got to give them a little plug because I just think it's great. Um, so furthermore, why should you listen to me? I've performed over 1,700 unique simulation projects there. So I actually haven't even updated this in several months, but I have a log where I track the projects I've worked on, and I can sort and filter and figure out how many unique simulation projects I've been involved with. And yeah, that's over 1,700 at this point. So I've seen and done quite a bit of mold flow, so I have a decent background on this stuff. So getting into the meat and potatoes of what we're talking about here today, I want to ask you guys a question. Have you ever noticed if you look around a hot drop that's applied to a part, that there's not really any evidence of the heat from that hot manifold on the part itself? So you look in this case, we've got that same kind of teal color all the way around that hot drop, 125 degrees Fahrenheit. No real evidence of any kind of heat concentration associated with that hot drop. I thought this was a little bit strange, so I started digging into it a little bit more, and that's kind of what we're going to be going through today. So if we look at the anatomy of a typical hot drop, we've got this cross section here taken from uh, one of our Beaumont books uh, that John Beaumont's written. We've got the hot plastic melt stream there in red, encased in steel, and then surrounded by these heater bands. In this configuration, this is an externally heated hot manifold, which is probably the most common configuration. There are some different options, but around that heater band, we have this air gap. So that's going to be really critical in understanding Moldflow's assumptions about the heat from this manifold and why it may or may not be considered. So we have this air gap, and let's get into a little bit of background about thermal conductivity, air versus steel, and why these assumptions are being made. So if we look at thermal conductivity, we look at the units of that, it's watts per meter Kelvin. So what that's basically telling us is how much energy in watts is being transferred through a thickness in meters per a given temperature delta across the medium. So you've got a difference in temperature, which allows for heat transfer. You've got some thickness of material, and you've got how much energy is being transferred. Now, the most important thing is to compare the thermal conductivity of air versus steel to understand why these assumptions are being made. So if we look at P20 steel, thermal conductivity of 29 watts per meter Kelvin, air 0.02 watts per meter Kelvin. So P20 steel is 1,450 times more conductive than air. So in comparison, air is practically a perfect insulator. It doesn't really transfer much heat relative to the P20 steel. So by default, given these conditions, Moldflow assumes that the hot gate and runner are insulated with a constant flux of 10 watts per meter squared. So flux is just a measure of how much heat is being transferred. So watts per meter squared. So how much energy per given area. So the question is that a reasonable assumption? Is it reasonable to assume that basically all of the heat from the hot manifold is insulated from the mold? And can we affect results if we dig into this a little bit deeper? So we need to look at some heat fluxes here to get a sense of what heat transfer is like in a couple different scenarios. So if we look at the first image here, from the hot manifold into the surrounding steel, we've got that 10 watts per meter squared number that we discussed. So that's what Moldflow is assuming how much heat is being transferred from that hot drop into the surrounding steel. Now, if we compare the plastic part in the mold cavity to steel, we've got 9,770 watts per meter squared. So 977 times the heat flux. So the plastic is putting a lot of heat energy into the mold steel in the areas that aren't considered insulated, but relative to the hot manifold system with that 10 watts per meter squared assumption, of course, it's a lot higher heat. So the question is, what about the gate? So if we look at that same cross section of an externally heated hot nozzle, we see that air gap coming down, but eventually we see that that actually stops and we have hot plastic making contact with steel. So the question is, doesn't that put some heat energy into the mold? Isn't that going to heat that steel in that area? And shouldn't we see that in some of the cooling results or simulation? And if we do get a hold of that heat, does that affect our results? Does it affect warpage? In particular, does that affect cycle times within simulation? Let's take a look at a cross section from an actual 3D mold here instead of just some textbook stuff. We'll see again, you've got hot plastic making direct contact with the steel. I've traced out the hot manifold channel with this sort of split ported tip, and you can see that that hot plastic is making contact with that steel at that gate. The air gap is over here, but the gate itself is making some contact with the steel. Just another view here highlighting that area that I'm talking about. So all of this hot plastic is close to steel, making contact with steel, and should be transferring heat. Again, just to reiterate, Moldflow is assuming 10 watts per meter squared for these gate elements, just like the fully insulated hot runner element. So over here on the right, you can see those heat fluxes from a default Moldflow simulation, and it's just 10, 10, 10 all the way down. And then the part, of course, instantly cranks up to 9,077. The question is it a safe assumption? So what would happen if we remove this assumption? Would it affect temperature of flow front? Would pressures be affected? Volumetric shrinkage, warpage, and others. There's a lot of different things that it could affect when you have uh, possibly a significant change in heat profile within an area of this mold cavity. So let's get into a case study here. Just a little bit of background on process and material. This is polypropylene material. The process details themselves are not super important, but just a little bit of background. Melt temp 420, pretty typical for polypropylene. Water temperatures, a little bit of differential water here. A side 80, B side 100 degrees Fahrenheit, and pretty typical temperatures for polypropylene again. Injection time 4.2 seconds, switching over 98% full cavity. Packing with 5,000 psi for 30 seconds, cooling for 6 seconds. Part solidifies at 38 seconds, and total cycle time 40 seconds. And another point to make here is that it is a glass fiber filled material. So if we look at a cross section through the mold, I'm just showing that this is actually a 3D FEM mold mesh. So we've meshed the entire uh, mold cavity with 3D elements to try and do our best to capture this effect. All right, so now we're going to get into how we can manipulate some of these parameters to try and capture the heat flux from that hot gate. So if we look at the default hot gate property here, we can see these heat loss into mold options. And by default, it's set to automatic, which gives a constant flux of, again, that 10 watts per meter squared. So one method to change this insulating property and allow some of the heat from that hot gate to actually make it into the mold steel is to change this heat loss into mold property to insulating properties, edit the insulation, and put in this air gap value and basically make it zero. So this is 0.00025. You're just making it extremely small. So you're basically saying it's effectively like steel on steel contact at that point, plastic on steel contact at that point. The other method I was curious about was to do this constant flux method. So taking that heat loss into mold, changing it from automatic or insulating properties and making it constant flux and grabbing that flux from some reference data. So you'll have to run a preliminary cooling analysis to see what kind of flux you get from the part to the mold steel, which in this case was 9,770, and input that into the hot gate. So just jumping right into some results here, we've got iteration one, which is the default mold flow assumption, iteration two, which is that air gap method, the very small air gap method, and then iteration three, which is the constant flux method. So what you'll notice right away is that the air gap method iteration two starts to give us a pretty significant increase in mold steel temperature there. We can see the colors. What we'll typically do with mold flow results is scale them all the same, so they'll have the same max and the same min. That way the colors can tell the story for us. So you see more yellow, more red, more dark green here with iteration two, and magnitudes there uh, about 228 degrees Fahrenheit, just selecting a point, compared to 122 degrees Fahrenheit for iteration one. So almost double the mold temperature around that hot gate. So we're actually picking up on that heat transfer. Iteration three, only a couple degrees Fahrenheit. So that particular flux doesn't seem to be enough to really give us the type of heat that we might be expecting from that gate. Jumping into a fill time animation here, just to confirm if there's really going to be any change to the fill time result, we can see that there's really not much here. The filling trend is practically identical between the three iterations. Looking at temperature at flow front as another result, again, just having it scaled the same, you can see the color distribution practically identical. Uh, there's no discernible difference on temperature at flow front. Now, here's where things start to get interesting. If we look at average volumetric shrinkage, we'll note that iteration two starts to show significantly higher volumetric shrinkage around that gate. You can see again the color distribution. We've got a higher amount of greens and dark reds around that gate and just a different trend overall. And we're definitely picking up on some elevated shrinkage, which is what we would expect because the mold's a lot hotter there. The question is it going to affect the warpage? Getting into the warpage results here. So we have iteration one looking at -2 millimeters in the dark blue versus iteration two, where we're at 1.8 millimeters. So overall trend is very similar. You can kind of see the same kind of color pattern. Iteration three, we already know isn't really doing much to give us that heat, so we're not as interested in those results at this point. But with iteration two, we are definitely seeing some change to the warpage magnitudes, actually a little bit less warpage on the outside of the part there. So it's an interesting result. So that's just one example. I wanted to go ahead and run a couple more studies and see if we could get more significant differences in different case studies. So here's case study number two, which I'll call iteration four and iteration five. Again, Moldflow default on the left And now just looking at that air gap method on the right, in this case, the model is materials high density polyethylene, got a 3D tetrahedral part mesh, and again, the 3D FEM mold on this particular example, which is basically the top of a bucket style part. So again, just some additional material details. It's a high quality material file with fully measured PVT and mechanicals. Jumping right into some results, again, looking at part temperature here. Again, you see a significant increase in part temperatures associated with that air gap methodology from 158 to 325 degrees Fahrenheit. So again, almost double. And clearly, color distribution around that entire drop has changed. You're getting an actual heat concentration, which is what we would expect. Temperature flow front, again, not a big change here, not that interesting. But again, looking at volumetric shrinkage here, we've gone from kind of a nominal yellow to all dark red around that center gate, 20.3% versus 21.7%. So we've seen about 1.5% increase in local volumetric shrinkage. If we look at the Z deflection here, now we're starting to see a little bit more significant of a trend change and along with some magnitude changes here. So you can see iteration 4 on the left, a little bit of a lighter blue there in the center of the park compared to iteration 5, which is kind of all dark blue in that center. It's all shrinking downward much more significantly than it is for iteration 4. And yeah, obviously magnitude's pretty significantly different, 10.2 versus 11.7. So we're again picking up on a higher degree of warpage, Z deflection in this case, with the air gap method. Let's get into another case study here. Again, iteration 6 on the left is the default, iteration 7 on the right is the air gap method. And we're looking at the snuff camlet. So this is like if you picture a can of Copenhagen or something, it's got that little plastic lid. This is that lid. So relatively small part. What I wanted to do was look at a relatively small part because those other two examples we looked at are kind of larger parts. And I figured the smaller the part is, the more that heat concentration from that gate is going to influence the total properties. So in this case, polypropylene material, 3D tetrahedral model again, and running beam cooling in this case. So not even doing the FEM mesh in this case. Curious to see with traditional beam cooling, could we still pick up on the same effect? And yeah, not really having any trouble picking up on that. You can see we've got 92 Fahrenheit on the left versus 236 on the right, more than double in this case. So we're getting a lot of heat concentration around that gate, as we would expect. Temperature flow front, again, no big difference there. But volumetric shrinkage starts to get very interesting. We've got 2.8% versus 4.1% on the right. Um, and overall trends are just very different. You've got this all kind of nominal teal color for iteration 6, but for iteration 7, we've got a big dark green circle in the center of the part, a big dark red eye right at the gate, so getting a lot more volumetric shrinkage through the center of that part. Magnitude's a lot different, 2.8% versus 4.1%. So we're seeing some big differences on this one, which is, like I said, what I would expect for smaller parts. Finally, looking at Z warpage on this, you can see iteration 6 on the left, the default assumption, we're getting practically zero warpage. I mean, 0.02 millimeters in the center there, 0 millimeters on the outside. So basically no warpage to speak of. But once we account for the heat from that drop, we see negative 0.5 millimeters in the center of the part and negative 0.11 on the outside of the part. So we actually start to see some differences in warpage in the part and actually pick up on warpage of the part. So here's an example where you simply wouldn't see this warpage at all had you not accounted for the heat from that gate. So it can definitely make a big difference. And this is a really good example of that. Now I'm looking at this a little bit differently. I've flipped the part around and I've introduced a scaling factor to kind of exaggerate the warpage trend. And you can see that we have on the left, basically, you don't really see any deflection at all. And on the right, you see a big big bowing out in the center of the part there. It's scale times 10, so it's exaggerated, but it just makes the point that we're actually picking up on some warpage with this methodology. Now, there is some future work to be done. Um, the best thing to do would be to do a real world correlation study, measure some actual mold steel temperatures and compare to simulation outputs. Um, so, run a probe on the actual mold steel and compare those outputs to simulation. Um, Transient simulations, so looking at not just cycle average as is the default with Moldflow, but looking at transient cooling across the cycle and perhaps even multi-cycle transient simulations to see if this heat is building up over time, is that going to further affect the warpage and really make a big difference? Um, Full 3D tetrahedral hot runner versus beam. So these studies were all done with beam hot runners, but it'd be interesting to see for a full 3D hot runner model at tetrahedrals. Would it make more of a difference? How would that affect things? Buckling warpage analysis, be interesting to do some eigenvalue comparisons between using this factor and not. And just other materials, just running a variety of different materials on a variety of different parts, more correlation. And lastly, just more simulations and correlating to actual warpage. All the situations where Moldflow maybe wasn't correlating exactly with the warpage trend, let's introduce this factor and see if that improves the results and see if that actually gets us better correlation. So I think there's definitely some studies out there where these effects were missed and possibly leading to uh, inferior simulation results. Thanks again for your time, and we'll be opening up for any questions here right after this.